welcome. My name is Neil Chopra. I'm going to be giving a presentation on thermodynamics today. So to begin, thermodynamics is the study of work, heat, and energy on a system. More specifically, thermodynamics involves the study of flow of heat or energy. Thermodynamics is most commonly utilized to describe large-scale observations. It basically establishes the concept that mechanical work and heat are equivalent, and that energy is conserved. As a bit more of an introduction, all thermodynamics can be expressed in terms of four quantities. We have temperature, variable T in units of Kelvin, internal energy, variable E, units of joules. We have entropy, variable S, units of joules per Kelvin, and we have heat, which is variable Q in units of joules. So the first law of thermodynamics. The first law of thermodynamics is usually referred to as the law of conservation of energy. The first law states that any changes in internal energy of a system is equal to the heat added to the system minus the work done by the system. It also states that the overall total energy of the universe remains constant. This theorem can be expressed in equation form, and it's as follows. We have delta U equals Q minus W, where Q equals heat, W equals work. I have an image here that I retrieved from NASA's webpage on the first law. It states that any thermodynamic system in an equilibrium state possesses a state variable called the internal energy, or E. Between any two equilibrium states, the change in internal energy is equal to the difference of the heat transfer into the system and the work done by the system. So more about internal energy. I have a quote here from William Glassley from Geothermal Energy, which I have used as a reference for this. If a system is completely isolated from its surroundings, then at any set of conditions, the internal energy of a defined system is fixed and depends only on the properties of the materials of which the system is composed. It establishes the significance of knowing the internal energy at the endpoints of a process. It also establishes that the difference between these 2 points determines how much energy is required to heat a space, generate power, or cool a room. It also assumes that the path followed to get from the initial states to the final states has no significance in the change in internal energy. There's an equation at the bottom, which is the change in internal energy equals the final internal energy minus the initial, or EF minus EI. Now we're getting into pressure volume work. Any change in internal energy of a system is a result of the work done to it and the heat that is either added or removed from a system. This is something we talked about earlier. We have the equation again for the change in internal energy is work plus heat. At the bottom here, though, we have a derivative of this equation that we can utilize if only pressure and volume are the ones changing to create mechanical work. We can utilize the equation at the bottom if only pressure and volume are variable within this equation. We have W equals negative P times V2 minus V1, which also equals negative P times delta V, where P is pressure, V2 and V1 are volumes at specific states, and delta V is the difference between those two. Now we get into enthalpy. The enthalpy of a substance is a measure of the energy that is released or absorbed by the substance when bonds are broken and formed during a reaction. When bonds are formed, energy is released. In order to break bonds, energy must be absorbed. We have an equation here at the bottom for the change in enthalpy, which is equal to the change in enthalpy of bonds broken minus the change in enthalpy of the bonds formed. Now getting on to efficiency. The thermal efficiency of a heat engine is as follows in this equation. The efficiency equals negative W divided by Q, which is the amount of work divided by heat. An important note, it's impossible for any system to have an efficiency of 100% or E equals to 1. This is an ideal situation, but we can't really reach that. Now talking about the Carnot cycle, this is more about heat engines, concept theorized by Nicolas Leonard Sadi Carnot, a French engineer. It idealized the theory of a thermodynamic engine and allows for determination of the efficiency using the ideal gas law, or PV equals nRT. The area under the PV curve represents the quantity of work done in a cycle. The area inside the four curves represents the net work done by the engine in only one cycle. When the curve goes from right to left, the work is negative. Getting to heat capacity. Heat capacity is the amount of heat required to raise a certain mass of a material by a certain temperature. C equals to dq over dt is the equation for this, where dq and dt are differential changes in heat and temperature, or the difference between the two. Second law of thermodynamics. The second law of thermodynamics introduces the entropy variable, or ds, a measure of disorder within a system. This is also shown as delta S in this equation, which is delta S equals delta Q over delta T, where delta Q is the change in heat over the temperature. We can also utilize a Gibbs free energy equation, which we will talk about later. The second law helps us determine the preferred direction of a process or reaction. A reversible process is one that can change state and then return to the original state. All natural processes are reversible. If it's a spontaneous reaction, the entropy difference will be greater than 0. If it's at equilibrium, the entropy difference will be 0. This is another image retrieved from NASA on the second law of thermodynamics. There exists a useful thermodynamic variable called entropy, or S. A natural process that starts in one equilibrium state and ends in another will go in that direction that causes the entropy of the system plus the environment to increase for an irreversible process and to remain constant for a reversible process. Gibbs free energy can be used to calculate the maximum amount of reversible work that may be performed by a thermodynamic system at constant pressure and temperature. Specifically, this is non-expansion work that can be extracted from a thermodynamically closed system. Here we have the equation for Gibbs free energy, where delta G PT is the Gibbs energy at P and T, a given pressure and temperature. We have delta H P1 T1, which is the enthalpy at some standard state, usually selected to be 1 bar pressure and 25 degrees Celsius as temperature. We have delta S P1 T1, which is the entropy at the standard state. We have delta Cp, which is a constant pressure heat capacity. And we have delta V, which is the change in volume. And that's everything. Thank you for listening.